The objective of this lab is to demonstrate the reversal technique for straightness of motion measurements. Machine slides or carriages are theoretically single degree of freedom devices permitted to move along only one axis. In practice, measurable motion occurs in all directions, thereby introducing discrepancies between the desired and actual positions. In precision processes such as the fabrication of optics, these errors can destroy the integrity of the product. Therefore, a method for quantifying machines' motion errors is necessary to determine that machine's suitability for a given operation. Furthermore, error measurement is necessary before any compensation schemes can be effected. Many measurement procedures involve the comparison of the specimen to some reference standard. An object's mass is often measured by balancing the object with an artifact of known mass, or the length of a workpiece is determined by comparison to a scaled rule. In such a manner, the straightness of a carriage or slide can be measured by comparing the slide's travel to a reference straight edge. Imagine a point P fixed on the carriage and another point Q1 located on the reference surface such that the line PQ1 is orthogonal to the axis of the carriage. The length of the line segment PQ1 is recorded for this first x-axis position. The carriage is now translated a specified increment delta x to the second x-axis position, where a second line PQ2 is constructed from point P to point Q2. The length of the second line segment is then recorded for the second x-axis position. As the carriage continues to move along its axis, line segments are constructed and their lengths are recorded for the successive x-axis positions. After measuring the full range of carriage travel, the length variations of the line segments can be plotted versus their respective x-axis positions. This graph represents the error in the carriage motion relative to the reference straight edge. In theory, the reference straight edge contains no straightness errors. In reality, some errors remain in even the most precise standards. Therefore, straightness measurements made with a reference straight edge will include both slide and straight edge errors. Ideally, the error in the straight edge is much less than the error in the slide travel. In some cases where this condition is satisfied, the error in the straight edge might even be ignored. However, when the two errors are of the same order of magnitude, the straight edge error cannot be overlooked. This ultra-precision lathe or diamond turning machine achieves two-axis motion through two orthogonally configured hydrostatic bearing slides. The spindle and workpiece ride on the z-axis slide. The diamond cutting tool rides on the x-axis slide. The tool engages the workpiece at the horizontal center line of the spindle. Therefore, the straightness of the tool motion in that horizontal plane is the unknown to be determined. Straightness errors for these diamond turning machines, or DTMs, are typically less than 1 micrometer over 25 millimeters of carriage travel. Since this motion error is not sufficiently greater than the 45 nanometers of straight edge error, the straight edge error cannot be ignored. The principle of reversal allows the total error to be separated into the slide error and the straight edge error components. The basis of this method is that in one step the data is collected such that the error components are subtractive, while in the other step the error components are additive. The collected data sets can then be combined either by addition or subtraction and adjusted to show the error for either component. As the name indicates, reversal is a technique where the relative senses of the slide and straight edge errors are reversed. In this first step, the errors are additive, that is, positive z motion error of the slide and a protrusion out of the straight edge both cause the measured separation distance to decrease. In the second step, the straight edge protrusion still causes the gap to decrease, while the same positive Z motion error of the slide causes the gap to increase. The straightness error in the straight edge can be obtained by adding the measured error from each step, then dividing the result by 2. The straightness error in the slide can be obtained by subtracting the step 2 error from the step 1 error, then dividing the result by 2. Using the reversal technique and some basic hardware, straightness measurements will be made for both the reference straight edge and 225 millimeters of the x-axis carriage travel. A metal-plated Zero-Dur optical straight edge will be used as the reference. The Z-motion error of the x-axis slide and the irregularities in the reference surface will be measured with the capacitance gauge. The non-contacting probe will sense changes in the distance between the probe tip and the straight edge by measuring capacitance changes between the target area on the reference surface and the probe's 1.7 millimeter diameter sensing area. The separation changes can be read from an analog display or can be expressed as an analog signal voltage. If the original or nominal separation is mechanically or electrically zeroed, the display needle would indicate 0 by remaining in the center of the scale, and the output signal voltage would be 0. A decrease in the separation would result in the display needle moving to the right of center by an amount corresponding to the decrease. The output signal voltage would become a positive value determined by the output factor of 2.5 micrometers per volt. An increase in the separation beyond the nominal separation would result in the display needle moving to the left of center by an amount corresponding to the increase. The output signal voltage would become a negative value determined by the output factor of 2.5 micrometers per volt. The analog voltage signal from the capacitance gauge will be sent to an analog input on the DTM controller. Inside the DTM controller, the analog signal will be converted to digital values. The DTM controller, which has resident data gathering routines, will record the x-axis positions and their respective digital voltages. Later, these voltage levels will be converted to distances with the 2.5 micrometer scaling factor. Zero-Dur is a glass material with a very low coefficient of thermal expansion. This characteristic makes Zero-Dur a very attractive material for high-precision applications requiring dimensional stability. The reference surface of the straight edge has been ground, lapped, and polished to be both smooth and flat. The error in the straight edge is specified as 45 nanometers over the 300 millimeters of length. The reference surface has been metal plated to facilitate use with a capacitance gauge. The straight edge will be held in a kinematic cradle. The straight edge should be level and its center line should be located at the height of the spindle and tool center lines. The design of the kinematic cradle allows the straight edge to be supported by the minimal 6 forces, thereby avoiding overconstraint and the resultant variable deflections and positioning uncertainty. In this manner, the kinematic cradle helps to ensure that the reference surface is uniformly positioned for both steps. An important requirement for the reversal procedure is that the capacitance gauge head must sense along the same path on the reference surface during both measurement steps. Although the averaging nature of the capacitance gauge head does reduce the effects of path differences, reasonable efforts should be made to minimize these path differences. For example, if the capacitance gauge was positioned at the straight edge center line to within 15% of the radius of the probe's sensing area, the step 1 path and the step 2 path would have 90% overlap. The reversal yoke, which should be level as well as orthogonal to the straight edge, allows the capacitance gauge head to be consistently positioned for steps 1 and 2. Note that the mounting fixtures have been designed with large cross sections and numerous gusset plates to minimize deflections and vibration. Precision measurements demand vibration-resistant fixtures. Thermal growth of fixtures and components can also be a problem. For example, temperature gradients from handling can cause thermal expansion of the capacitance gauge stand, thereby introducing measurement error. For precision measurements, wear gloves, minimize handling, and allow time for thermal equilibration. Sensor cables should be well secured and free of tension. Furthermore, sensor cables should be routed clear of other cables, which could introduce electrical noise into the output signal voltage. Recapping the setup, the kinematic cradle is mounted to the stationary z-axis such that the horizontal center line of the straight edge coincides with the horizontal center line of the spindle. The holder for the capacitance gauge head is mounted to the x-axis, the carriage whose straightness is to be determined. The capacitance gauge head, or probe, is positioned in the holder's reversal yoke at the center line of the straight edge such that it senses changes in the separation between the probe tip and the reference surface of the straight edge. A decrease in the separation gap causes an increase in the output voltage, and an increase in the separation gap causes a decrease in the output voltage. In this first configuration, the straightness errors in the slide and the straight edge are additive. Using the reference systems shown, a protrusion out of the reference surface in the negative z direction and the motion of the x-axis slide in the positive z direction both cause the gap to decrease and the signal voltage to increase. Using this first setup, the probe is moved from x equals 0 along the length of the reference straight edge to the position x equal 225 millimeters. The carriage speed is 12.5 millimeters per minute. Capacitance gauge and x-axis position data are collected every millisecond. 4,800 samples are averaged to yield one data point for each 1 millimeter interval of the x-axis travel. The carriage location and error data are recorded into a data file. The carriage is returned to its original position of x equals 0. The straight edge is rotated 180 degrees around its major axis so that the reference surface is now facing the positive z direction. Care must be taken to ensure that the straight edge is positioned in the same location as before. The probe is repositioned in the reversal yoke so that it again senses the reference surface. In this second configuration, the straightness errors in the slide and the straight edge are subtractive. With the straight edge and the probe reversed, that same protrusion out of the reference surface, now in the positive z direction, still causes the gap to decrease, while the same motion of the x-axis slide in the positive z direction now causes the gap to increase. The signal voltage is now the difference between the two phenomena rather than the sum. Again, the probe is moved along the length of the reference straight edge, and data